Thank you, Yuval. So happy birthday a little early to Russ. I'm happy to be here. And I want to tell you about an old problem, algorithms with noisy comparisons. Let me first give you the setting. There's an old story from the 1990s, some work by Feiger, Peleg, Raghavan, and Upfal, a paper entitled Computing with Noisy Comparisons. Very similar. What kind of problems are they working on in that paper? They work on a model where when you do comparisons, you may have errors. For example, is 25 greater than 18? You ask an oracle, you don't have direct access to the values, they're hidden, and the answer is correct with probability, let's say, 3/4, and something else with the complementary probability. What was the motivation for this study in the 1990s? Then they said fault tolerance is an important consideration in large systems. They wanted to devise robust algorithms that work despite unreliable information without sending out the faulty components. And that's it. I think I quoted the entire motivation of that paper. Now we skip ahead by a little over 20 years. In 2016, Braverman, Mao, Weinberg. They have a paper entitled Parallel Algorithms for Select and Partition with Noisy Comparisons. What is their model for noisy comparisons? Is 25 greater than 18? You have an oracle. With probability, say, 3/4, it answers the truth. With probability 1/4, it says something else. Very similar. Actually, it's the same. Same model of accessing data, noisy comparisons. But the setting is a little different now. So first, this is longer. There's a longer story. These are my invention, 25 and 18. They talk about peer grading, crowdsourcing. These concepts did not exist then in the 1990s. So they say multiple rounds of interaction are costly. Queried information may be inconsistent. So what they think of is, say, peer grading.
There are lazy professors doing peer grading existed for,
All right, crowdsourcing. You want to make up your mind. You outsource some questions. You get some answers. And then you have to decide what to do next, if you're going to ask another round of questions or if you stop there. OK. So 2 different venues to get to a similar model and similar flavored questions. Slightly different because there's a difference of emphasis. Braverman, Mao, and Weinberg are interested in minimizing the number of queries to try to do a computation, get a reliable result based on unreliable comparisons. But their priority is to have few rounds of interaction. So they're primarily interested in parallel algorithms. Feiger, Peleg, Raghavan, and Upfal happen to be interested in parallel algorithms, but their primary motivation is to minimize the number of queries. Okay, so it's a difference of emphasis. Okay, so 2 generations, 1 family of problems. Let me look at one basic question. Selecting the maximum. Selecting the maximum of n numbers. Without errors, you can do it with n-1 comparisons. The naive approach to fault tolerance is to just use redundancy. So ask every comparison many times so that you're confident that the result is correct. And this way you can simulate the noiseless case with noisy comparisons. OK. So repeat each comparison, log n over delta times. You do a majority vote. And then your answer is correct with probably at least delta over n, your choice. And then after you've done n comparisons, your final output will be correct with probability at least 1 minus delta.
So do you mean it's incorrect with probability delta?
Yeah. Incorrect with probability delta over n.
Delta is close to n.
Delta in my vocabulary, delta tends to go to 0. It might be a constant, but
Just trying to save the slide.
Maybe n also goes to 0.
okay, different worlds. All right. Okay. So the first contribution of Feiger, Pelag, Ragavan, and Upfall was to show that you could do better than this. You didn't have to pay this blow up, this log n additional factor. And here is the first algorithm they suggested. They say it bears a remarkable resemblance to the NBA championship. Teams pair up and play a game in the first round. The winners pair up and play 3 games at the next, 5 in the third, and so on. A, 3, 5. What is that sequence? 1, 3, 5, 7, and so on. Okay. So this is what you do. You do these comparisons, keep the winner, do these comparisons, but more times, keep the winner, do these comparisons, and then you have the final winner. Okay.
For the sake of accuracy, I think even in 1994, that's not the way the NBA championship.
Actually, so this, if you want the result to be accurate with probability 1 minus delta, then you, 1 arrow means log of 1 over delta comparisons. Okay, so now you pay n times log of 1 over delta and not log n log n. And you have log n rounds. NBA, I looked that up on Wikipedia. NBA, B means basketball. I always forget, is it basketball, is it football, is it, but this is basketball. And on Wikipedia, they say the rules have changed over the years. But in 1951, in 1951, division semifinals, best of 3. Division finals, best of 5. NBA finals, best of 7. Okay. Thank you, James. Okay. An alternative algorithm was suggested by them of the form a best of 3. So what you do is you initially pretend you have a hierarchy, and you position your nodes n over 2 at the bottom, n over 4 at the level above, and 1 on top. You pretend this is the correct ordering, that is, the top is better than S2-1, every node is better than S2-1, and then all you have to do is check. You check it by disjoint sets of triplets. For each triplet, what you do is you compare the 3 elements, and if the maximum of the 3 is not on top, you switch them so that the maximum ends up being on top of the triangle. You alternate odd and even rounds, odd and even levels. You do this, repeat this log n times, alternating, and then the maximum has magically ended up on top. Okay, so that's the an alternative approach to computing the maximum. Okay, so about log n rounds, but good for a number of queries. Okay, here come Braverman, Mao, and Weinberg. They say they start by asking, we want a constant number of rounds, or the 1 rounds, because we're doing a crowdsourcing or peer grading. You don't want to do many assignments. How many queries can we get away with if we just do all the 1 rounds? They show that, they observe that you can do it with 3 rounds and n log n comparisons. Okay, n log n comparisons as we had with the naive approach, but just 3 rounds instead of log n. How do you do it? So here it is. You take a set, a random sample of size square root n. You do every comparison, pairwise comparison inside S, repeating them log n times to compute, to deduce the maximum. This only takes one round. You can do everything in parallel. Okay, you have this maximum S. Then you take every element of your initial set X, you compare it to S to decide whether it's greater or less than, repeating log n times. In parallel, this is just a single round. Then you keep the ones that have the majority, that appears to be greater than S. That's a set of about square root of n elements. And round 3, you do all pairwise comparisons with an x prime, repeating log n times to find and output the maximum. Okay, so this is sort of the basic, one step above naive.
It's a little bit resemble the secondary problem?
In a way, yes, because S is an element of small rank. Yes. So first you have a first phase where you find an element of small rank. This is like the observation phase of a circuitry problem when you find somebody who's pretty good. And then second phase, except it's not online, so you can look at everybody. Okay. So then they go to the other opposite, the other end of a spectrum. They say, let's say we want a linear number of comparisons. How few rounds can we get away with? Okay, how few rounds? Turns out you can get away with log n rounds. Here's what you're going to do. So initially, you pick a random subset of, say, n over log n elements. You find the maximum element of S. Okay, you have few enough elements there that in 3 rounds, you have few enough elements here that this part only costs you order n. Okay, now you have an element that is pretty good, rank about log n. Now you start from all the elements. It's a similar idea. You will trim them to a smaller and smaller set gradually in log n rounds. And then until you have a set at time t equals log n of candidates that is small enough that you can, again, in 3 rounds, find the maximum with only order n comparisons. And at every step, what you do is you compare every remaining candidate to S, log of 1 over delta times, and you discard the elements that, let's see, you only keep the elements that have won the majority of comparisons since the beginning of time. Okay. So every x that is not greater than S performs a biased work that is biased downwards, so you get a chance to eliminate it at every round, and after log n rounds, enough are eliminated that you can finish naively. Okay. So good. So now you don't need log n rounds. Log n rounds suffice, even if you want a linear number of comparisons. Can you do better than this? Well, actually, yes. Yes, there's an algorithm that is better. This was like a first attempt to reduce the number of rounds. But in fact, it's possible to have an algorithm that has a trade-off between number of rounds and number of queries. That is the following. Let's say for your queries, you want to limit yourself to n log b over delta queries for some value b. Okay? So you want to limit yourself to q queries, and that defines b. Then it's possible to do it with a number of rounds that is log star b of n plus a constant. What is log star b of n? It's the opposite of the tower of b elements. So if n is equal to b to the b to the b to the b, then the height of the tower is r, where r is log star bn. Okay, so if you limit your queries to q, then that defines b, and from b you get the number of rounds. That's the trade-off between number of rounds and queries. What is the algorithm that achieves this trade-off? It is the following. So initial part is similar. You take a random subset of, say, n to the 2/3 or whatever, little O of n elements. In 3 rounds and few comparisons, you find its maximum element. You use it to prune the set, and then in the end, in a constant number of rounds and order n comparisons, you will find the maximum of what's left. What's the difference? The difference between this algorithm and the previous one is the number of iterations is no longer log n, but log star b of n. The number of times we do a comparison is no longer log of 1 over delta, no longer a constant, but it's this quantity. It's a quantity which is chosen so that at every step, the number of queries will be q over 2, q over 4, q over 8, and so on. And then what do? You eliminate from X all those who did not win against your apparent approximate maximum, the majority of those comparisons. Okay, so this is a simple variation that enables you to go from a log n to a log star base b of n. Now this is about elegance in probability, this workshop. And you could say, well, that's kind of awkward. That's not very elegant. So let me try to rewrite it. Let's say the number of rounds is r. Then how many queries do you need to get the correct answer? You'll need about n log n, where the number of logs is about r plus order 1. R plus order 1. Okay, I don't know if that looks more elegant. Okay. Here's another way to make this elegant. Let's move to lower bounds. Here's the lower bound. For any b, we must have at least n log b queries or at least log star bn minus order 1 rounds. So that means that except for this plus order 1, the algorithm I sketched earlier achieves the optimal trade-off. Yes? Okay, so now that's more elegant. Feiger, Peleg, Ragavan, Upfall. The old paper. And BMW. Yes. Okay. So this was the upper bound. This is lower bound proving tightness. There's another lower bound that is also kind of interesting that was proved 25 years ago, which is that if you don't pay attention to the number of rounds, but only to the queries, then you have to pay at least n log of 1 over delta queries if you want the output to be correct with probability 1 minus delta. Okay, so how do these work? Let me first talk about this n log of 1 over delta lower bound. First, you start by changing the model. We were working in the comparison model. We're going to change. Let's say that the error probabilities are 1/9 and 8/9. Okay. So instead, we use the noisy value model, where you ask for the value of an item. The value of an item, you ask an oracle, and it tells you 25 with probability 8/9, and whatever it wants with probability 1/9. Maybe the same thing, maybe something different. Okay, that's a different model of accessing data. You ask for the values of the data. Why is this better for proving lower bounds? Because when you do comparisons, you do it between pairs of elements. So if you want to look at all the information you have so far about all your elements, you have all these informations about pairs, so you have a graph. So it's complicated. But here, these are just unary functions. You just ask information about a single element. And so you have the information you have so far is divided into one piece for each element. So that's much easier to deal with. Okay. Now I claim that if there's an algorithm that works in a noisy value model, then it gives you an algorithm in a noisy comparison model. And that's sort of obvious, because you can simulate a comparison. Why? If you want to simulate a comparison, is x greater than y? You ask, what is the value of x? You get an answer that is correct with probably 8/9. What is the value of y? You get an answer that is correct with probably 8/9. Compare those two values and use that to answer yes or no to this comparison. Now, if these values are correct with probably 8/9, then the result of a comparison will be correct with probably at least 2/3. Okay. So you can simulate an algorithm in one model by an algorithm in the other model. And therefore, if you want to prove a lower bound in the noisy comparison model, it suffices to prove a lower bound in the noisy value model. Okay. So the lower bound is a decision tree argument. Here is the family of instances that will be difficult for the algorithm to distinguish, to discern. One input consists of all zeros. The other inputs consist of all zeros except there's a single place where there's a 1. Xj equals 1.
Sarah, maybe I'm just like, but I missed something in the logic. Can you go back?
Yep.
So you prove that if it's easy to do the noisy value, then it's easy, then there is a fast algorithm for noisy comparison. And then
So the lower bound for
and then you want to
lower bound for the noisy.
So I'm going to prove that
It's hard the noisy query. Then it implies that the other one is also hard.
but that's not the direction. Yeah, no problem.
Yeah.
Suppose you have an algorithm that works quickly for noisy comparison. It also works quickly for noisy value.
What you stated is the other thing, right? She said if there is an algorithm for
If there is a lower bound for the noisy query,
value
it
model.
extends to the noisy.
I cannot answer these kind of questions in real time.
Positive. If you have a quick algorithm for noisy comparison, you have a algorithm for noisy value. If that's impossible.
A lower bound for the noisy value implies a lower bound for the noisy query.
right, but that's not what.
That's what's written here. It's just written in a different way. To prove a lower bound to noisy query, it suffices to prove a lower bound to noisy value.
But that's not. So the lemma says if there's an upper bound in the noisy value, then there's an upper bound in the noisy comparison.
No.
If there's a fast algorithm for noisy value.
Second one.
The lemma, what does the lemma say? The lemma says, the first lemma in the top says if there's an algorithm in noisy value, you have a fast.
Okay. No, the lemma is, but I'm looking at the corollary. So the lemma
The
should
corollary is a corollary to the left.
If there is a fast algorithm for noisy comparison, then there is a fast algorithm for noisy value. Okay? And then the corollary is exactly what it is.
It's okay.
The lemma.
I think the lemma is okay.
as stated. She proves that if there's an algorithm for noisy value, she gets a quick algorithm for noisy comparison.
Therefore, if there is a law,
No. It proves what the inventor did.
you can continue.
I think I will continue. I cannot answer these questions, this kind of questions in real time. Sorry, this is the kind of things where I cannot answer it in real time. Sorry. But Gil says.
The equivalence of a statement and its contrapositive is like the first logical equivalence that the human mind has problems with.
I know. I've been having trouble with this for more than 30 years. Okay, I will proceed. Okay, so the entry is either all zeros or all zeros with a position that has a 1 somewhere. Okay, so now if you look at the decision tree, the algorithm is executed, and you look at the path in the execution. Is what is x3 equal to? 0. What is x1 equals to? 1, and so on. You get to some other question, maybe what is x1 equal to? Again, you get a 0, and then the algorithm stops and says max equals 0. Okay, so that's to distinguish this input from all those inputs where the max is equal to 1. Okay, so this is one execution. If you look at all possible executions, you can look at all possible leaves, and let's look at all the leaves that are labeled 0. The max is 0. If the input is all zeros, the probability that we reach such a leaf must be at least 1 minus delta. That's what it means for the algorithm to be correct on that input with probably 1 minus delta. On the other hand, there's one thing I stated that was backwards. Yes. Okay.
So the problem was that the lemma was stated backwards. Its proof was the proof was correct for the corollary. So the corollary is fine. The lemma was stated backwards.
Okay. Good. Thank you. Okay. On the other hand, if there's a 1 somewhere, if your input has a 1 in a j position, then the probability that we reach a leaf labeled 0 must be at most delta. Okay, that's what it means for the algorithm to be correct when the input has a 1 somewhere. Okay. Now, these two inputs are not very different. We don't have much of a chance to distinguish between them as we go down this execution, this path in the decision tree. In fact, we only have a chance to distinguish when we query the jth element. When we query the jth element, we have an 8/9 probability of having the answer one way and 1/9 the other way, and it goes the other way around for these two things. Okay, so that's the only difference. So, okay, so the probability of reaching this set of leaves is at least 1 minus delta in one case, at most delta in the other case. But following a particular path, L, from the root to a leaf when xj equals 1 versus when it's all zeros, it differs by only 1/9 over 8/9, 1/8, to the number of times in that execution we looked at bit element xj. Okay, RJL, number of queries of element j along the path L. Okay, and so if you look at the sum over all possible positions, all j's, of the probability of reaching one of those 0 leaves given you have a 1 in position j, then, so sum over path L, for each path L, you can replace the probability given xj equals 1 by the probability given it's all zeros with a 1/8 to the RJL. And these RJLs, these are the number of queries of element xj along the path. We know that the sum is the depth of a tree. the length of the execution. It's like Q, at most Q.
And that inequality, J was fixed on the left, but it's summed over on the right? No, up.
There's a sum over J here.
Oh, sorry.
And this sum is, I should have repeated it here. Okay. This is the first time I'm giving this talk, so the slides are not yet perfect. Elegant. Okay. And by convexity, the worst case is when all the RGLs are equal and equal to their average. So that gives you a bound. Now you plug that in. You say the probability of getting S, given that it's all zeros, is at least 1 minus delta. The other probability is at most delta. You have a sum over J and delta. And you get an inequality. When you solve, it gives you the n log of 1 over delta. So that's the proof. That's a simple calculation from once you have decided to work on the value model. Okay. So that doesn't tell you anything about rounds. It's all adaptive. You don't know anything about how long it takes if you do a parallel algorithm. So how do you prove the other bound? How are you going to prove a trade-off between rounds and queries? What helps you is that during a given round, all the queries are done at the same time without any, they have to be done independently of one another, each of them independent of the result for the others. So, okay. So now let me look at the lower bound for rounds versus queries. We use what Karp calls the little birdie principle. What is the little birdie principle? If you give extra information to the algorithm, it cannot hurt. So let's give extra information to the algorithm, and it cannot hurt the algorithm. And it gives you more structure to the problem until the problem becomes simple enough that we'll just have to do a little calculation and we'll be done.
Why do you call it the little birdie?
You know these pictures where there's an angel sitting on your shoulder or a devil and whispering things into your ear? That's the little birdie. It's sitting on your shoulder and saying, I have this extra hint to tell you. Okay, little birdie principle, very useful. Always correct. You just have to trust the little birdie. And very useful for lower bounds. Okay, so in this lower bound, here's what the adversary is going to do. If the true value is 1, so we're trying to find a 1 hidden among many zeros. If the value of the element queried is 1, the adversary will say the truth. Or I'll say 1, 1, 1, 1, 1. If there's a 0, if the element queried is a 0, then it will lie and say 1 with probably 1/9. So at any time, if you look at the elements that have been queried, if you get a 1, 1, 1, 1, 1, 0, you know this can be discarded. As soon as you get a 0, you can discard the element. It's not what you're looking for. But if you have an element that says where your answers were 1, 1, 1, 1, 1, and another one that says 1, 1, 1, 1, 1, then you don't know. The one could be hiding at one place or the other. So all these entries will look exactly the same, at least if we've had the same number of queries to them. Okay, we have no information that enables us to distinguish, and so we'll have to go until we have a single element that is all ones. Okay. Let's assume for a contradiction that the number of queries is less than Cn log b for our lower bound, and C is 0.00001. Okay, there should be an omega here. I forgot to put the constant. Okay. At the beginning of a given round T, you have an element still in the running, candidates to be the maximum, the hidden one. So at the beginning of round 1, S0 consists of n elements, all the elements. Okay. We're going to say for free, we'll allow, the little body will say, actually, I'm going to allow you Q queries, not just at every round, not just overall, but at every round. Okay. So these Q queries, they can be spread between these ST-1 elements. And by Markov's inequality, only a few of them are queried a lot more than the average. Okay. The little body will say, if an element is queried more than this many times, I will tell you its true value. Okay? I will consider, okay, I give up on this, I reveal the truth. And what about the majority of the elements? They're queried fewer times than this. Then the little body will say, all right, I will give you answers to this threshold number of queries. Okay, so it pads the answers and gives you enough answers to enough queries that everybody who is not, for whom you don't know yet the truth, has been queried exactly the same number of times. Okay, so what happens at the end of round T? Then everybody who has been queried many times, you know the truth. If one of them is the 1, you're done. You say, okay, I found my 1, the max is 1. If none of them is the 1, then maybe one of them is hiding in here. Okay. And, all right. If you take one of those people, anybody who answered 0 at least once, you can discard it. But you're left with some fraction of those who only answered 1 all along. So these are elements that have all been queried the same number of times during round T. And at the end of round T, all the answers were all 1s. They're indistinguishable. And now we proceed to round T plus 1 with that set of elements. How does this diminish? How long does it take before we have a single element left? That's the only question. And the answer is a little calculation gives you a recurrence, and a little algebra gives you that bound. Okay, the rest is just math. That's what I say in computer science talks. I say, now it's just math.
We say it's just computing. So.
It's just a calculation. Okay. So what have we learned? We have proved this lower bound. We have proved that the algorithm that gave this trade-off was optimal. Okay. So let me conclude with a couple of remarks. Let me go back to the lower bound. The lower bound, the n log of 1 over delta lower bound. The hard instance there consisted of trying to distinguish between an input where everything is 0 and an input where there's a 1 hidden somewhere. Okay, but what if we know that there is a 1 hidden somewhere, and the task is to find that 1? That is, what if the input cannot be all zeros? Now the problem is, given a 1, that there's a 1 somewhere, find it. Now we know the input except for the location of this 1. Then the lower bound does not hold. This lower bound, this n log of 1 over delta lower bound, is not valid. So what this suggests is,
Why is that?
because this lower bound, it needs to have inputs where you have all zeros. See, if your inputs are all zeros except there's a 1 somewhere, and you want to distinguish between having a 1 in position I and a 1 in position j, then you can't just say, look at position I.
But you mean there's no proof of the lower bound, or there's
When you say the lower bound does not hold, you mean the proof doesn't hold, or the lower bound really doesn't hold?
The proof does not hold.
But I understand something basic. If in the original case with the all zeros, suppose I assume the all zeros is not there, and I do what you're saying, so that's
so I run the algorithm, and it's supposed to end and give me some. So I'm just assuming I'm not in that case. It's supposed to produce the location of the
Right.
location of the one.
So that particular algorithm works in order n log of 1 over delta, but is it optimal? I don't know. Maybe if you know there's a 1.
No, suppose you have a wonderful algorithm that works, that's faster. Now, what if you apply it in this supposed hard case where you have the zero? Just apply the algorithm anyway. Assume you're in the good case when there's vector zeros, it's not there. And it's supposed to tell you a place where the 1 is. And then you just go and examine.
Yes, I know what you mean.
that-
I know
that
your question.
location and in
Yes.
another log 1 over delta comparison.
But there it is.
Not n times log 1 over delta, just log 1 over delta. Just check that location against other random locations.
Yes, but then if the answer is no, actually this is not a 1, it's a 0, then what do you infer?
It's all zeros. We're making this an interactive proof for you.
Yes, I understand.
But the proof only restricted to this set of instances, and if you want a general low bound should apply to all instances. So therefore, it's not clear that what Yuval is saying.
I mean, to find a...
No, but she said that this,
Okay, maybe.
if you had this, the proof, there was a lower bound proof for this collection, and then,
Yes,
but eliminating this one.
eliminating just one instance. Okay, I need one more. Okay, so...
Well, all we know is
So-
the failure probability if there is a 1. You don't know the failure probability if there isn't a 1.
No, her model had failure probability in 1/9 worse.
No. The supposed algorithm when there's a 1.
So we can think about it.
That has some failure probability.
Okay, well, maybe we'll continue.
Yeah, let me just give my last slide, and then I will, because this is really a special case of my last slide, and maybe my transition was not the best, which is about instance optimality, which is about the following. You have your input, elements from some universe, A1, AN, given to you, a sequence of inputs. There's several ways to prove a lower bound. One is to say that these could have several different values. And the other one is, for a general problem now, is to say, even if the algorithm knows the multiset, if it doesn't know the order in which the elements are given in the input, then the cost is still high. Okay. And in other words, what is the price of not knowing the input ordering versus the price of not knowing the input values? There are some problems where these two things are different. Some instances are easy when the values are well chosen. And then you can design an algorithm that is instance optimal. That is, it's going to adjust to the values and give you a complexity that matches the lower bound. Okay? That is, the only difficulty is the difficulty coming from the random permutation of the input ordering. So this is one thing that has been studied for two-dimensional problems, but not so much for one-dimensional problems having to do with sorting, selection, median, and maximum. Okay, that's it.